Hello, everybody. I'm Alireza Javaheri, and today I want to present our new paper, AVID Variational Inference Deliberation for Meta Learning. Okay, first of all, we start with the difference between machine learning algorithms and humans. As you know, today machine learning requires training with a large number of samples. And if we train, for example, a deep learning model to perform task A, and we have a new task B that is closely related to A, we can use the same model. We need to train the model from scratch for task B. So today's the machine learning algorithms or deep learning models are single task. They can't train on just a single task. But in the other hand, humans can learn new concepts and skill much faster and more efficiently. Human can generalize learning to multiple concepts and learn from there. Okay, let's check the difference between multitask learning and meta learning. In multitask learning, we solve all tasks more quickly and proficiently together than learning them independently. But in meta learning, we use the prior experience from solving previous tasks to solve a new unseen task. As you can see here is example for example of reinforcement learning. For example, in multitask reinforcement learning, we have some tasks and we want to perform this task together more quickly. But on the other hand, in meta learning, here in this example, meta reinforcement learning, we have some tasks and we want to model learn from there and gain some experience and gain some knowledge can adapt to a new task easily. The task might be unseen in the data set. Okay, what is a supervised task? A task type R called a task type R contain some data, some label, and a proper loss function. And the corresponding data set is our DTR and DTest. In the meta learning problem, we want to solve tile test given data from tile 1 to tile n. As you can see here, for example, it's a deep learning model, and he has a input X. For example, in this example, we have the input is an image, and we have an output, a label Y, and we have some parameter of the model we show with theta, and the model is with f theta y given x. Some terminology is checked here. As meta learning consists of two parts, meta training and meta testing. And in each part, we have support set, DA train, and also a query set, DA test. We use the support set to update the base learner's weights, and we use the query set to update meta parameters so that our model can provide optimized initial weights for the base learner. Also, we have two other terminology. Car-shot learning means training the model use car sample, and the n way, it means having n different classes in the data set. And for example, when we said one shot 5 way, it means in the data set there are only 5 classes, and in each class there is example just one picture or data. Or when we said 5 way 5 shots, it means we have just 5 class, and in each class we have just 5 data, or for example 5 image. Okay, in 5-shot classification, the model will overfit massively since the training data is not sufficient. We need to use other data in order to learn more efficiently when encountering a 5-shot task. So the problem can be solved by incorporating other meta-training data when we want to solve a new task. The meta-train consists of n dataset, and each dataset contains car data points. We notice that we should incorporate additional data to perform new tasks, but it is inefficient to carry the meta-train in each task. So we will use some parameters that contain everything we need to know about the meta-train to solve new tasks more efficiently. Let's dive into our proposed model, which is one of the most powerful algorithms according to the results. Our proposed model is called AVID, a variational inference deliberation for meta-learning. Recent gradient-based models only succeed in solving tasks with a very similar structure, since they adapt the model with a shared meta-parameter across all tasks. Also, the high-dimensional parameter space of gradient-based model hinder them from achieving their full potential in low data regimes. Our proposed model bypasses the aforementioned limitations by leveraging Bayesian algorithms as well as clustering input tasks. As you see in this figure, we perform clustering. As you see in this picture, we perform clustering to find the cluster to which the input the task belongs. This empowers the model to handle various tasks from different distributions. Also, we have used a variational Bayesian method to elevate the model's uncertainty in order to increase the generalization of the model. Now, let's explore the AVID architecture. As you see, this model consists of 4 parts. The first part is the task representation, in which we have used a recurrent autoencoder to obtain the task representation. The second part is the encoding part, the encoding network, which receives the task representation as input and maps it to a low-dimensional space. And then a hierarchically structured clustering algorithm is utilized to find the cluster of the input task. And we will use this information to enrich the latent code here. And then we use the network G. To create a Gaussian distribution and get a sample from this distribution to perform the next stage. The third part is decoding network, which is responsible for producing task-specific parameters in order to adopt the meta parameters for the base learning F, which you can see in this figure. And the final stage is meta learning strategy, which consists of 2 parts. In the inner loop adaptation, we perform a few steps of gradient descent to adapt the base learner to the new task. In the outer loop adaptation, we update the parameters of the main network to produce the optimized meta parameters for the base learning. Here we have compared the result obtained from AVID and other baseline models in 5-way 1-shot task and 5-way 5-shot task. And it is clear our model outperforms other baseline model, which confirms the efficiency of the AVID. And thanks. If you have any question, you can find me at this email.